Question number 2. We're now looking at a reaction between nitrogen dioxide and carbon monoxide. And we're given some data. Again, I see what type of data this is. They gave me time. They gave me concentration. This is an integrated rate law problem. So we're going to graph the data. We're going to make those 3 graphs. And based upon those 3 graphs, we should be able to identify the order with respect to the NO2. All right, so go ahead and do that. Take a look there in your PDF file that you have open. Take a look at those 3 graphs that we've produced. Locate the straight line and see if you can determine what order the reactant NO2 is. And then see if you can write the rate law from that. The graph that produces the straight line is the one with the 1/, concentration, the reciprocal. That means it is second order with respect to NO2. So my answer for A would be, this is second order with respect to NO2, because the graph, or you can use the word the plot, of 1/, concentration versus time is a straight line with a constant slope. I've answered the question. I've justified my answer using the data presented to me in the question. For part B, the rate law would be rate equals baby K concentration of NO2 squared, because it's second order. Now, for those of you looking at the chemical reaction, you might be scratching your head. You're like, wait a minute. What about the other reactants in the reaction, the carbon monoxide? Right? Because usually in that rate law, we have all of the reactants in the rate law. Now, if it's 0th order, obviously it doesn't appear in the rate law, but we haven't even looked at the other reactant. We do this sometimes. We set up the experiment in a way that we pretty much keep the concentration of one of the reactants constant. And that's what we're doing here for the carbon monoxide. It doesn't affect your answer, but I just wanted to clarify why we are ignoring the carbon monoxide for right now. It doesn't say it in the question, but the experimental design would be this. And I know there's another reactant here. I'm talking about the CO, carbon monoxide. The reason why we're ignoring it for right now is because when we do this experiment, we're going to make sure that the concentration of the carbon monoxide is significantly higher than the concentration of the NO2. And so essentially what we're doing is we're holding the concentration of carbon monoxide constant throughout the experiment. Because it's so high in concentration, I know we're using a little bit of it, but because a little bit is such a small percentage of the really big amount, its concentration is basically remaining constant at that high level. And so we see how the concentration of the reactant we care about is changing over time. And that's why we're kind of ignoring the carbon monoxide right now. The student would then have to follow up and do a similar experiment, flipping it around, where they would have to hold the concentration of NO2 really high, and then monitor the amount of carbon monoxide. Okay, but for right now, we're not going that in depth. So we have our rate law. Part C, calculate the rate constant, which is K, which is slope. So to calculate your K, choose any 2 points from your data table. Doesn't matter which 2, we should all get the same answers, or roughly the same answers. So because the graph that produced the straight line is the reciprocal graph, I only need to look at the reciprocal column and the time column. Pick 2 points, and I'm just going to pick the first 2, x1, that's my x2, that's my y1, that's my y2. Keep it simple. Okay. And so we're going to do y2 minus y1 divided by x2 over x1. Okay, calculating rise over run. And so here's my work for that. Going to get a K value of 2.1025 times 10 to the negative 4. Because this is second order, our unit is going to be 1 over molarity to the first. And the unit again is seconds for time. All right, so part D, integrated rate law time. So that means y equals mx plus b. So plug in what we have on the y, plug in what we have on the x, and you plug in your y-intercept. Okay, so our variables are 1 over the concentration. We got a positive K value because we have a positive slope. And again, this is straight from your notes, just substituting in the NO2. Then for part E, I know that I'm going to have to use the integrated rate law because look at the problem. They're asking you to solve for concentration, and the information you're given is time. Time and concentration means use integrated rate law. So that's exactly what we're going to do. We're going to plug in our information into the integrated rate law. And this is what you're going to get. I'm taking our K answer, plugging it in. The specific time they want is the 2.70 times 10 to the 4th power seconds. And then my y-intercept here is 2, because I'm looking at that data table. I go all the way back up to that data table, and I'm looking at the reciprocal column at time 0 as a value of 2. And so my goal now becomes I need to solve for the square brackets of NO2. So we're going to clean up the right-hand side here. All right, so this ends up becoming 1 over concentration is equal to 7.67675. And now I need to solve for concentration. I can't leave it as 1 over concentration. I need that to read concentration. So the easiest thing to do is flip the fractions. Okay. Flip it. So when you flip, you're going to end up putting NO2 over 1. But if I flip the left-hand side, flip, I got to flip the right-hand side. Okay, take the reciprocal of it. So the concentration of NO2 is equal to 1 over the 7.67675. Solve for that, and you're going to get a concentration of 0.130 molar as your answer.